Bueno, buenas tardes. Good afternoon. It's my pleasure just to welcome you to this public defense of the doctoral thesis of Natalia Ormeño. Firstly, allow me to introduce the member of this committee, Associate Professor Ignasi Cires from the University of Barcelona, and the full Professor Karin Groenen Serrano from the University Paul Sabatier, Toulouse. And I am Cristina Saez Jimenez from the University of Castilla-La Mancha. Well, as you know, this session will be structured in different parts. Firstly, Natalia is going to present the main result of this research entitled Electrochemical Removal of Antibiotics and Multidrug-Resistant Bacteria using Graphene-Sponge electrodes. That was carried out under the supervision of Jelena Radjenovic and Joaquin Comas. That's right, no? And well, I think that is your, well, after this presentation, we will have a period just for the discussion, just to comment the main aspect of your research with the member of this committee. And without further delay, I think that Natalia, it's your turn. You can start presenting during around 40 or 45 minutes your research work, okay?
Thank you.
Okay, I think.
Good afternoon. My name is Natalia Ormeño, and I'm going to present my PhD with the title Electrochemical Removal of Antibiotics and Multidrug-Resistant Bacteria using Graphene-Sponge electrodes. This presentation is divided into 5 main different points: a brief introduction, some specific objectives, the different materials and methods which were employed during the experimental part, the most relevant results, and the main conclusions. How do antibiotics end up in our aquifers? Antibiotics are frequently consumed by humans and also in veterinary medicine. And a significant percentage of these antibiotics is not metabolized and is excreted. In case of humans, these excretions goes to the wastewater treatment plant, where they are not completely degraded. These leftovers through the wastewater treatment plant's effluents are discharged into the natural aqueous environment. In case of veterinary medicine, this excretion goes directly to the environment, and due to different practices as manure spreading, this contamination is spread into soils and ending up into natural aqueous environment. From there, this water is treated in the drinking water treatment plant, where a significant percentage of these contaminants are eliminated. However, the most important consequence of the wide use of antibiotics is the antibiotic resistance, which is when a bacteria no longer responds to the antibiotic designed for killing them. There are three main focuses of contamination in case of humans: pharmaceutical industry, hospitals, because they accumulate large amount of antibiotics and they are discharge these antibiotics directly to the urban network without any previous treatment, but also the individual consumption. But how do we consume antibiotics? There are different inequalities between the global north and the global south countries, not only in the access, but also in the rate of consumption, being the north global the major consumer. Also the fact that in the healthy system, it's really common the inappropriate use of antibiotics is also an important topic. In case of animals, there are different ways to use antibiotics. Therapeutical doses, which are focused on treat a specific disease, metaphylatic and preventive use, which is basically to control or prevent an infection, and as a growth promoter, which is an unnecessary way to feed antibiotics to the animals in order to increase the weight of them. This practice appeared in 1950, and even though it was banned by the European Union in 2006, and in case of the preventive use in 2022, our actual model based on intensive farming, which is characterized by the overcrowding of and public welfare of animals, is not only an ethical questionable model, but also induced to the spreading of these contaminations, because the infections are usually more common and the demand of antibiotics increase. So the problem is still persistent. During this work, we were focused on 5 different antibiotics belonging to different families of antibiotics. In case of macrolides, we were using erythromycin and roxithromycin. In case of sulfonamides, sulfamethoxazole, and we also choose trimethoprim because it's usually administered with sulfamethoxazole, and ofloxacin as a model of compound, as a model of fluoroquinolones, sorry. We decided to focus on those contaminants because they are commonly used in human and veterinary medicine, and therefore they are frequently detected in the aquifers in concentrations ranging from nanograms per micrograms per liter. The fact that they are persistent and bioaccumulated because of their chemical stability and poor biodegradability. And also because the different physicochemical properties, which give us to have a wide perspective of our electrochemical treatment. But we were also focused our investigation in inactivation of bacteria. So we have to distinguish between 2 primary categories of bacteria, gram-negative and gram-positive, which are, as you will see in this slide, different in the structure. In case of gram-negative, they contain an outer membrane, which is formed by phospholipids with a hydrophilic head and hydrophobic tail, and in between the cytoplasmatic membrane and the outer membrane, a thinner peptidoglycan. In case of gram-positive bacteria, they do not contain the outer membrane, however, they present a thicker peptidoglycan layer. But how the bacteria become antibiotic-resistant bacteria? Some bacteria, they are intrinsically resistant to some antibiotics, and this resistance is transferred through vertical gene transfer, which is basically through the cell division. On the other hand, other bacteria, they acquire this resistance. There are different pathways, different ways to acquire this resistance. As an example of it is the transformation pathway, which means when a bacteria physically enters in contact with a free genetic mobile part, acquiring the information of this free genetic mobile part. As I was mentioned during the introduction, the fate of antibiotics and antibiotic-resistant bacteria end up in the drinking water treatment plants. We can distinguish 2 different processes for treating drinking water treatment plants. From one side, conventional process, for example, coagulation, sedimentation, and filtration, which present the main goal of eliminate the solid part and the turbidity of water. And then the disinfection units. However, all these processes are not sufficient for a complete removal of the contaminants. Therefore, we need additional treatments, as for example, the advanced treatment processes. We can advanced treatment processes as, for example, advanced filtrations, which is divided into microfiltration or ultrafiltration, depending on the contaminant. In case of ultrafiltration, is to retain viruses and bacteria, and microfiltration, some organic and solid parts. The advanced oxidation processes, we can, in this, in here, we can, we have different treatment, as for example, ozone-based treatment, UV-based treatment, and other emerging technologies as phenton, photophenton, catalysis, photocatalysis, sorry, and electrochemical oxidation process. And for more water quality, for more quality waters, also nanofiltration and reverse osmosis. But let's come back to the advanced oxidation processes, because it's the focus of our PhD, of my PhD. So according to all these mentioned processes, they usually present some limitations, as for example, the higher cost, as the case of ozone-based process or UV-based process. On the other hand, some specific quality in the water matrix, as the case of UV is limited by the turbidity, or phenton and photophenton by the pH. But among all those mentioned treatment, they present one major limitation, except for the electrochemical oxidation process, is the necessity of addition of chemicals to the treatment. For that reason, we decided to focus our attention in electrochemical oxidation treatment, which are electrochemical oxidation treatments are based on the induction of current into the working electrode, which is the anode, to oxidize different contaminants or pathogens, and when simultaneously the reduction reaction is occurred in the cathode. This oxidation process can be performed in two different ways. Direct anodic oxidation, in which the contaminant is adsorbed onto the surface and directly eliminated. This process is mainly limited by the diffusion of pollutants from the bulk solution to the anode and the electrocatalytic activity of the anode. On the other hand, the indirect anodic oxidation via different oxidant species, as for example, hydroxy radicals, ozone, or peroxide. This indirect anodic oxidation can be performed in two different pathways when the oxidant species is stable in the bulk solution, or when this oxidant species is adsorbed onto the surface. From all these mentioned oxidant species, the most powerful one is the hydroxy radicals, because of its high potential, oxidation potential. In this slide, the advantage and challenge of the electrochemical oxidation treatment are presented. As advantage, we can say that, as it was mentioned before, the in situ production of oxidant species, so we don't need additional chemicals. Also, the possibility to decentralize the treatment, and the robust operation and the wide variability of conditions in which we can work, in which we can perform our treatment. On the other hand, they present some disadvantages, as for example, the high cost of the electrode, especially in most commonly used anodes as boron-doped diamond. Also, the mass transfer limitations when 2D materials, and the chlorine toxic byproduct formations, which usually occurs in water matrix with a high concentration of chloride, which is indirectly oxidized into chlorine, and with the organic matter can produce chlorate and perchlorate, which are toxic byproducts. For that reason, to overcome all these limitations, in our researching work, we designed a 3D graphene-based sponge electrode, which is totally inert to chlorine formation and really cost-effective. Therefore, the research aim of this work is the synthesis of 3D graphene-based sponge doped with boron, nitrogen, and sulfur, and they used in a flow-through reactor to evaluate the elimination of antibiotics and antibiotic-resistant bacteria. In the first chapter of this study, we assessed the electrochemical degradation of 4 commonly used antibiotics using boron as a dopant in the anode and nitrogen in the cathode in low conductivity electrolyte. In the second chapter, we investigate the electrochemical removal of 5 different antimicrobials and a multidrug-resistant gram-negative bacteria, using, in that case, a sulfur functionalization of the reduced graphene oxide to enhance the electrolyte-electrode interaction. And finally, in the third one, we explored the electrochemical oxidation process for the inactivation of a multidrug-resistant gram-positive bacteria using, again, sulfur-reduced graphene oxide, and we compare the effectiveness of this treatment in case of with our previous investigation of the inactivation of the gram-negative bacteria. The synthesis of our sponge, it was performed according to this diagram. We were using mineral wool as the skeleton of our sponge, which is quite stable because of its covalent bond carbon silicon. We soak this mineral wool into the solution functionalized with boron, nitrogen, and sulfur, and we place it into a hydrothermal treatment for 12 hours at 180 degrees. After this, we used the electrode and spike into a stainless steel current feeder. A complete material characterization was performed in all the different chapters. The setup of the electrochemical oxidation treatment is presented here, and the mother solution was prepared using 2 different electrolytes, 10 millimolar phosphate buffer and drinking water. The initial condition of antibiotics were 0.2 micromolars, and in case of bacteria, approximately 10 to 7 colony-forming units per milliliter. We were sampling in 3 different points during the initial open circuit conditions in order to study the absorption of antibiotics or also the elimination, inactivation of bacteria, then when the application of current, and during the final open circuit condition to evaluate as well if we were electrosorbing our contaminants. The analytical method in case of bacteria, as it's shown in the presentation, was performed by serial dilutions, which were afterwards filtered and plated into agar plates. They were incubated overnight at 37 degrees, and after this we were manually counting the colonies. In case of antibiotics, the determination of the concentration of antibiotics was performed by liquid chromatography and mass spectroscopy. Other parameters, as the oxidant species and the energy consumption and energy per order, as well as the electrochemically active surface area, were calculated as well. In the first study, the electrochemical degradation of a set of 4 commonly used antibiotics using Graphene-Sponge doped with boron was evaluated in a flow-through reactor. In the first point, we investigate the impact of different operational parameters. In the second point, we evaluate the ionic strength of the supporting electrolyte. And in the third point, we elucidate the transformation products of erythromycin as a model of compound. According to the results, and starting from the flow rate during the open circuit conditions, as we can see in this graph is represented the removal of the 4 study antibiotics. There are significant differences between the behavior, as for example, in case of sulfamethoxazole, which is poorly absorbed onto the sponge. This is probably a consequence of the electrostatic repulsion due to the negatively charged of the reduced graphene oxide and the negatively charged of sulfamethoxazole at neutral pH. On the contrary, ofloxacin is affected or governed by several interactions, are, for example, strong PP interactions between the molecule and also the different aromatic rings of the reduced graphene oxide, cation pi interactions, since it's presented at neutral pH as a switteronic molecule, and also different hydrogen bondings between the switteronic molecules, the different oxygen groups of the RGO and the molecule. In case of erythromycin, as we can see, it was a little bit more affected by the increase of the flow rate. This is probably a consequence of the weaker cation pi interaction between the positively charged antibiotic. In case of trimethoprim, quite similar to ofloxacin, it was almost completely absorbed in all studied flow rates. When the application of current, we could observe a detrimental impact in all cases of when we increase the flow rate. It's important to point out the case of sulfamethoxazole, which was previously almost poorly absorbed onto the sponge, and when the current was applied, especially in case of flow in medium and lower flow rates, almost completely eliminated. Sorry. Well, the elimination of those contaminants, as I was explaining during the introduction, can be produced through two different ways. Direct oxidation of the absorbed contaminant, which is really difficult to quantify in our scenario, and indirect oxidation through different oxidant species, which were quantified and we can see in this table. Even though those antibiotics are not kinetically affected by ozone, it's important to mention that anodically generated ozone and also cathodically produced peroxide are actively transformed in hydroxy radicals in the anode, and in case of the peroxide, in the inactive site of the cathode. So therefore, it seems that all these oxidant species are actively participating in the electrochemical elimination of antibiotics, not only hydroxy radicals. To investigate and confirm that we are not absorbing, not only absorbing our antibiotics, but also degrading them, the methanol extraction was performed in anode and cathode during the open circuit conditions only, and in anode and cathode when the current was applied. In this graph, we represent the milligrams of antibiotics per gram of electrode. This protocol, it was only valid for those antibiotics which were highly absorbed onto the sponge, as for example ofloxacin. According to the result, we could observe the significant difference between the concentration of ofloxacin in the anode during the open circuit condition and in the cathode during the open circuit conditions compared when they were anodically polarized, confirming that strongly absorbed antibiotics are clearly electrochemical degraded. And also the importance of the strong PP interactions, which reduce the mass transfer limitations and therefore favors the electrochemical oxidation of contaminants. to investigate the impact of the currents into all study antibiotics, we ran the treatment for 48 hours in order to get partial saturation of the sponge, and after this we applied the highest current into the reactor. According to this graph, we could observe that a gradually decrease of the concentrations in case of all study antibiotics till almost complete removal. Then, when the current was again switched off, antibiotics were again gradually increased in values lower than the open-circuit initial conditions, which means that we are degrading our contaminants and also regenerating the sponge. On the other hand, it's important to mention that the fact that the antibiotics, they didn't achieve the initial condition is probably a consequence of the capacitance of the electrodes. On the other hand, the energy per order was calculated, and according to the result, for the highest, in case of the highest current applied and a medium flow rate, and according to the result, we could observe as ofloxacin was the lowest value, which again highlighting the importance of an efficient absorption and interaction with the electrode. The evaluation of the ionic strength of the supporting electrolyte was also performed using the same experiments, but changing the background electrolyte from 10 millimolar phosphate buffer to drinking water. According to the result, we could observe as, in case of the trimetoprime and ofloxacin, which are highly absorbed onto the sponge, in drinking water, they were clearly affected. And this is probably a consequence of the lower conductivity of drinking water, which increase the electrical double layer thickness and avoid the direct contact or limit somehow the interaction with the antibiotics and the electrode. However, when the application of current was induced into the treatment, more than 70% of the removal was achieved, except for the case of trimetoprime. The elucidation of the transformation product using erythromycin as a model of compound was also performed. According to this result, 3 different transformation products were identified. The first one corresponds to the demethylation of the amino group in the desosamine sugar. The second one was a result of the elimination of hydroxy radicals, of this hydroxy radical in the desosamine sugar, and also the oxidation to a ketone group in the cladinose sugar. And the third one was a consequence of the cleavage of the cladinose sugar. From all these identified transformation products, just one of them still preserve the antibiotic, the group responsible of the antibiotic activity, and therefore is still a threat. The main findings of this study are the effective electrochemical oxidation of different target antibiotics was successfully achieved by doping with boron the anode and with nitrogen the cathode in low conductivity electrolytes. However, when we were using drinking water electrolyte, the performance was significantly worse. A strong PP interaction lead to a highly absorbed antibiotics, and therefore they are less limited by the mass transfer. In case of the application of current, it improves the removal of all these study antibiotics, even the one with low tendency to get absorbed onto the sponge. Then the methanol extraction confirmed the electrodegradation of the antibiotics, and different transformation products were successfully identified in case of erythromycin. In the second chapter, the electrochemical removal of antibiotics using a multidrug gram-negative resistant bacteria when sulfur was functionalized, it was studied in a flow-through reactor with NRGO as cathode. In the first part of this study, the surface and electrochemical characterization of the Graphene-Sponge was performed. Then we evaluate the inactivation of a multidrug-resistant bacteria, an E. coli, a gram-negative E. coli, and the electrochemical removal of different antibiotics from drinking water. Through XPs, different sulfur-containing groups were identified, as it can be seen in this table, different sulfur-containing groups were identified according to the results in this table. Well, it's important to mention that the carbon-oxygen ratio comparing RGO with SRGO is a little bit lower in case of SRGO, probably because of the different sulfur oxide containing groups in our sponge. On the other hand, the theta potential, contact angle, and the electrochemically active surface area were also performed. According to this result, more negative theta potential was observed in SRGO electrode, which is again probably a consequence of the appearance of different sulfur oxide containing groups. Also, as increase and decrease of the contact angle, which means that our material is more hydrophilic, and also slightly increase in comparison with RGO in case of the electrochemically active surface area, which probably is a consequence of the different S-functionalized group, which improve the anode electrolyte contact, enhancing as well the wettability. The electrochemical removal of a multidrug-resistant E. coli is presented in this slide. According to this result, we could observe as during the open circuit conditions, S-functionalization did not affect to the inactivation of bacteria. However, we achieved almost two-log removal, and probably a consequence of the membrane stress created by the direct contact of the bacteria with the nanosheet of our electrode. In case of when the current was applied, we could observe two different behaviors. In case of sulfur-reduced graphene oxide, an increase of the removal was observed, achieving 4.5 log inactivation of E. coli. However, on the contrary, in reduced graphene oxide, an increase of current induced to a detrimental impact of the inactivation of bacteria, which is probably a consequence of the creation of secondary reactions as oxygen bubbles, which are blocking the active site of the electrodes and directly affected to the effectiveness of our treatment. Electroporation was previously identified as one of the main mechanisms for bacteria inactivation. But typical electroporation treatment, they require higher potential gradients. However, in our study, we were able to eliminate a significant removal of bacteria, just requiring 3.6 and 3.8 volts per centimeter in case of SRGO and RGO respectively. This is probably a consequence of the nanostructure of our materials, which are able to enhance the electric field in the surface of the electrode, reducing the energy required. But not only electroporation, also different oxidant species are participating in the inactivation of bacteria, since they can diffuse into the cell membrane and disrupt the cell walls, inducing to a damage in the DNA and different enzymes causing the cell death. In this graph, we could see the log removal of the electrochemically treated samples, as well as the storing of the treated samples, because we would like to study also if a possible recovery of bacteria or regrowth of bacteria was occurring. According to these results, we could observe that not only bacteria were not recovering, an additional elimination was observed, leading to a 5.2 log removal of this pathogen, compared with a lower removal in case of reduced graphene oxide. The electrochemical elimination of antibiotics in drinking water was also evaluated, and according to the result and in line with the inactivation of bacteria, a higher removal was observed by functionalizing with sulfur during the open circuit conditions. It's important to mention, as in our previous study, ofloxacin was almost completely absorbed onto the sponge, and in case of sulfamethoxazole, it was poorly absorbed, which it was the same tendency as we were expecting. However, all these antibiotics, which were more affected by the limited absorption, a significant difference, it could be observed by the application, by the functionalization with sulfur, as we can see in this graph. Therefore, an enhancement of the absorption of antibiotics is attributed to the different sulfur oxide containing groups, which improve the surface hydrophilicity and wettability of the electrodes. When the application of current, it was kind of the same tendency. According to this, we could observe that even in the lowest conductivity, an important removal of all antibiotics was observed in case of SRGO and RGO. Comparing the case of sulfamethoxazole, which was limited absorbed, and in case of SRGO, it was completely absorbed, we could observe something really interesting. In case of SRGO, sulfamethoxazole needs more time to achieve the initial conditions, compared with RGO electrode. This is probably a consequence of an enhancement of the capacitance of our electrodes. So we can say that SRGO and RGO require lower energy consumption for the removal of more than 94% of all target antibiotics except for trimethoprim at the lowest current application. The key finding of this study were the sulfur functionalization in the Graphene-Sponge induced to the creation of different sulfur oxide containing groups, which enhance the hydrophilicity of the electrode and the wettability of the material. SRGO electrode achieved to a better removal in comparison with undoped reduced graphene oxide with lower energy consumption. In both scenarios and both cases, SRGO and RGO as an anode, no regrowth of bacteria was observed, and in case of SRGO, an activation of 5.2 log removal was achieved, confirming also the irreversible damage of the bacteria. Then sulfur functionalization also lead to a good absorption of the antibiotics and subsequent electrochemical degradation. In the third study, the irreversible inactivation of a multidrug-resistant gram-positive bacteria was evaluated using sulfur functionalization as an anode. In the first part, we evaluate the system in a single reactor. Then, in order to enhance the removal, we used two sequential reactors. And in order to lower the required energy of our system, we run the reactor in intermittent currents. The electrochemical inactivation of gram-positive bacteria in case of reduced graphene oxide and sulfur-reduced graphene oxide as an anode is compared in this graph. As was previously mentioned, we were also comparing the storing of the treated sample. According to the obtained result, during the open circuit conditions and in line with our previous study, we did not enhance the inactivation of bacteria, even functionalizing with sulfur. Then, in both cases, when the application of current and increase of current, it could observe an increase of the elimination of bacteria, which is slightly high in case of sulfur-reduced graphene oxide, leading to 3.3 log removal, comparing with 2.5 in case of reduced graphene oxide. Comparing this result with gram-positive bacteria, we could observe as exactly in the same operational conditions using the same materials and the same current, when we perform the electrochemical inactivation of an E. coli, which is a gram-negative bacteria, in compare with a gram-positive bacteria, double of removal was observed in the gram-negative one. This is directly a consequence of two different main gain points. The first one, the cell wall structure, which, as I was mentioned during the introduction, is different, and the outer membrane, in case of gram-negative bacteria, which is formed by different phospholipids, is kind of attracted to the Graphene-Sponge, to the hydrophobic domains of the Graphene-Sponge, but also the fact that the gram-positive bacteria present a thicker peptidoglycan layer, which makes this bacteria more resistant to the application of the electric field. Not only the difference in the cell structure, but also the shape is affecting the removal or the inactivation of both pathogens. Bacillus are previously reported to be more easily to eliminate it because they present more surface into contact with the electric field in comparison with coccus, which is the case of gram-positive bacteria. In order to enhance the removal of the Enterococcus, the gram-positive bacteria, we decided to run two sequential reactors. Regarding to the result, we could clearly observe how we are duplicating the inactivation of bacteria during the open circuit condition till achieve a completely removal of this pathogen. No variations in the different oxidants species by increase of the current also induced to probably the electroporation is the primary mechanism in the inactivation of those pathogens. To gain more insight into the irreparable damage of those bacteria, we investigate through scanning electron microscopy the different samples. According to these results, we could observe the influence sample, which is not affected, and the morphology is totally, is not damaged. In case of during the open circuit condition in which we have some bacteria, we could observe some bacteria which already present some lumps and different morphology in the surface. However, at the highest current applied, it's clearly presented the phenomenon, the electroporation phenomenon that I was explaining before, in which the internal part of the bacteria are leaking through the outside, leading to an almost complete removal of bacteria. To lowering the energy consumed by our system, we also investigate the inactivation treatment in intermittent current, comparing with continuous one. We were using an asymmetric and an asymmetric mode. Regarding to the result, we could observe as longer off pulses lead to a detrimental impact of the inactivation in both cases. However, in case of two sequential reactor, not only the symmetric but also the asymmetric lead to a detrimental impact of elimination of bacteria. However, in case of a single reactor, the asymmetrical one decreased the energy consumption from 2.7 to 1.8 kilowatts for approximately the same log removal. So the main conclusion of this study are presented here. We could say that the addition of sulfur again enhanced the removal efficiency of gram-positive bacteria comparing with undoped-reduced graphene oxide. Different not only in shape but also in the structural cell composition compromise the effectiveness of the treatment. Two sequential reactors lead to an almost complete elimination of gram-positive, in which no regrowth of bacteria was observed. Also, the irreparable damage was confirmed by scanning electron microscopy, and the application of intermittent current led to a lower energy consumption in case of a single reactor. Taking back the research aim of the project, which was the synthesis of different 3D graphene-sponge electrodes doped with boron, nitrogen, and sulfur to get a successful inactivation of antibiotics and bacteria, we could affirm that PRGO graphene-sponge successfully degrade the antibiotics in low conductivity electrolytes. The primary mechanisms were the absorption and further electrodegradation of, through direct or indirect oxidation of the contaminants, and different transformation products were confirming the participation of some oxidant species. In the second chapter, the synthesis of sulfur-reduced graphene oxide enhanced the hydrophilicity and wettability compared to previously synthesized boron-reduced graphene oxide, leading to a better contact between the contaminants and nodic surface. And different antibiotics and multidrug-resistant bacteria were successfully eliminated through direct and indirect oxidation in low conductivity electrolytes. And the main conclusion of the third chapter was the elimination of the possibility of the elimination of a gram-positive bacteria, which was almost completely eliminated by two sequential reactors. We also observed that difference in the cell structure and also the shape of bacteria clearly affect to the inactivation treatment, and we were able to lower the energy consumption by applying different intermittent currents. As a future perspective, I would like to point out the necessity of control and monitor the different transformation products, because in some cases, after the electrochemical oxidation treatment, there usually a release of this transformation product, which in some cases can be even more toxic than the parent compounds, and also the release of antibiotic-resistant genes, which are quite stable into the environment. On the other hand, the importance of reducing the energy consumption of these technologies through different strategies as modulating, integrating renewable energy source, and on the electrochemical treatment. and also the importance of understand some other ways to deal with intensive farming, intensive industries, because they are this kind of animal farming drives to antibiotic pollution into the environment. So it's important to highlight the necessity of different ways to, how can I say, go through other policies more respectful with the environment and more eco-friendly, I would say. And thank you for your attention. Yo me quedo aquí, ¿no?
Okay. Well, thank you, Natalia, for your presentation. Well, now it's time to engage with you and to discuss an aspect of your research. And the first will be your turn, Ignacio.
Okay, thank you, Cristina. Well, let me start by giving some thanks to Jelena for the invitation. Okay, it's my first time I met her in person, although we work on a very similar topic. Yeah, so the thesis has been really interesting. Okay, and that's why I have many questions. Yeah, so this is really an exam. Yeah, so I will consider the time. Yeah, let's see. If I take too much time, then let me know. Okay. So, well, first of all, let me, Natalia, congratulate you about the written report. Okay, it's very well written and it's easy to understand, and no big issues. Yeah, just some minor, well, mistyping, minor things. Yeah. So. And this is very important, no, in order to understand the topic, because even if it's related to what all of the three of us do, no, we are not maybe experts on disinfection or experts in this kind of specific pollutant or this kind of electrode, no, but overall we can follow quite well the meaning of all your explanations. But despite this, there are some points that, well, I find maybe confusing or maybe not sufficiently explained, or maybe there is not enough background. Yeah. So some of the questions are related to this, to lack of information maybe, and some other are more related to some doubts or interest on my side. Okay. So let me maybe start. Yeah. Your thesis has been 3 years, right, or 4?
No, more. This is the. It's already the 5. Okay. Yeah.
Okay. Well, I didn't mention, but I'm going to ask my questions in English just in order to allow Karin to understand. Okay. So, yeah, but I think it's okay for the audience. Okay. Yeah, in the introduction, I have maybe some very small questions. Yeah, maybe the main problem for me in the introduction is I like when the introductions like said very well, no, which is the situation currently. So compared to the literature and compared to the own group, okay. So it's not very clear to me which kind of work has been done before in the group, no? These materials, these dope materials applied to this kind of pollutants or to other pollutants with this kind of reactor or to other reactors.
Yeah.
So what's really new, original, okay?
Yeah.
And what's not based on some, because some explanation mechanisms you almost do not deep much, but tell that has been studied before, yeah?
Well, yeah, the Graphene-Sponge and this idea was performed by the research, our research group, even before I started my PhD. And after this, we were trying to optimize this electrode and also trying to synthesize in a way that we can improve the removal of, for example, in my case, I had been working with antibiotics, but in case of my college, they were also had been investigated on PFAS or pharmaceuticals or in disinfection. So according to this, we were designing the synthesis and yeah. But the base of the 3D sponges was before my I started here.
Okay. So then, in the mechanisms, because I mean, it's not very clear to me when the prevailing mechanisms is electroporation or when the oxidants, the cathodic or anodic oxidants, maybe have a role or a major role or a minor role. So
electroporation, in case of bacteria, I will say is kind of easy to understand that electroporation at least is an important mechanism because according to the scanning electron microscopy, you could clearly see what is electroporation, because I forgot to mention that is when a sufficient electric field creates some small pores on the cell of the bacteria where the internal part of the bacteria leaking through the outside. And this is something that we were confirming using the scanning electron microscopy. The participation of the oxidant species is more difficult to assess. I will say that are partially participating because, for example, in the two sequential reactors, I was explaining that since an increase of the current didn't enhance the concentration of oxidant species, probably the major mechanism is electroporation instead of oxidant species. But we cannot confirm which percentage of participation is in both cases.
Because when you present this, for example, this micrograph, okay, in SEM, and showing the electroporation effect and the cytoplasm exiting the cell, these images are at which time? Is a given time? Is at different times? Have you, or at different conditions? I mean, because here time, because it's in conditions.
It's in different conditions. We are running the reactor. In the case of this one, is just the sample without any treatment. Then we took a sample after the open circuit conditions, in which you can observe that some of bacteria, they are already damaged somehow, because we could see different lamps, and some others are completely intact. So it's kind of similar as our results during the open circuit conditions. And in case of this image, is the effluent after the highest application of current. So that's why in here it's kind of clear the electroporation mechanism.
Yeah, that's my question. If you have only micrograph at 43.5 ampere per square meter, or you have a set of conditions, and do you know that the mechanism changes depending on the current that you apply? Or to
yes, of course. We can confirm this according to the graph in the left. We could see as this is the highest current, but with the medium current, we do not achieve that much removal as the highest one. So, of course, it's affecting the disinfection treatment.
But you don't achieve that removal is because you don't produce enough oxidants or because you don't create enough pores on the bacteria?
Maybe because it probably something in between. Probably, but in this case, I think it's more related with the electric field is not enough to create these pores on the bacteria, because as I was mentioned also during this explanation, electroporations in general, in like typical electroporation treatments, usually require really high potential gradients, and so are directly dependent on the potential gradient. So probably if we are not applying enough potential, we are not able to inactivate all the bacteria. But according to the oxidant species, I mentioned in here we were determining the different oxidant species, and the variations were not that significant. So that's why we think that is the primary mechanism is more electroporation than the oxidant species.
Okay. That's what I have concluded, no? That electroporation is for you the prevailing mechanism. So then my second big question is, which is the criterion to choose this modification? No? Why sulfur, nitrogen, boron? Why those? Not dopings, but modifications, okay? And second is why choosing the boron modified as anode, no? The S modified as also anode, and the N modified as cathode. Why these selections?
In case of N doping, because according to the literature, we, as it was explaining, as it was shown in these schemes of the reactor, we are using always NRGO as a cathode. And this is because, according to the literature, the hydrogen peroxide as an oxidant species is favored produced when we are doping N with nitrogen, the reduced graphene oxide. So that's why we decided to synthesize this as a cathode. In case of boron, it was previously investigated to be kind of effective in case of some pharmaceuticals. So we were, as a first trial, working on that with this anode in case of in our first study. But since in our first study we could observe that using drinking water as a background electrolyte, we didn't have enough interaction between the electrolyte and the surface of the anode, we decided to try with sulfur in order to enhance the hydrophilicity and wettability of the electrode.
Okay, then you want a high wettability of the electrode,
yes,
in order to absorb the pollutants. But the mechanism will be electroporation, the main mechanism for the removal.
Well, but electroporation is just according to bacteria.
For the bacteria, yeah.
Yes,
I mean for the bacteria.
yes.
So, I mean, why do you care? What's the matter that the S-modified electrode is the anode or the cathode? I mean, what matters is to absorb the bacteria better. You can absorb on the cathode or on the anode?
No, in that case, it was increase the wettability and the interaction with the contaminants and the electrode. Because since we are enhancing the hydrophilicity of the material, contaminants, and when I say contaminants, I mean antibiotics and also pathogens, there is a better contact between the surface of the anode. And for example, during the open circuit conditions, as we could observe, we also are able to eliminate part of these pathogens through direct contact with the electrode. So it's also increasing the inactivation of bacteria as well as the absorption of contaminants. It's because of the...
But couldn't you find the same result using this as cathode?
Well, I didn't try SRGO as cathode, but in electrooxidation, mechanisms, we are most focused always on the anode, on the elimination through the anode and the oxidation of contaminants. So that's why we were like working on most focus on changing the synthesis in case of the anode. And during the whole thesis, we were using the same cathode in order to study what is happening in the oxidation.
No, I could understand this if the mechanism is an oxidation or electrooxidation that requires the absorption of the pollutant. But here you are always mentioning about ozone. I have understood that is the main pollutant also because it's the most concentrated that you are generating. So ozone-mediated oxidation seems more important than hydroxyl-mediated one, right?
Well, but ozone is sometimes also activated into hydroxy radicals. So in the end, ozone, for example, the kinetic rates of some of the pollutants is not that high with ozone than with hydroxy radicals, which means that they are easily attacked by hydroxy radicals compared with ozone. But ozone is also activated into hydroxy radicals.
But on the anode or in solution?
In the anodic, I don't know if in the bulk solution you mean, or?
Well, because you have a neutral pH, no? So when you alkalinize the solution, you tend to activate the ozone into hydroxyl radicals. So I'm not sure which is the role of the...
Yeah, occurs in the anode. In the anode, we are producing we are generating ozone, and this ozone is converted into hydroxy radicals. So it's participating. It's participating also in the. I don't know if maybe I am not that clear.
Okay. Well, I change direction, okay? In the experimental part, usually I like when the experimental part is like very detailed. Here I see that you describe several of the methods, but do not care about others. I mean, for example, XRD, BET, ICP, I don't know. There are some methods that are not in that section. Raman, for example, it doesn't appear there. But then appears in the papers, in the result sections. Why this?
Yeah, because some of them they were not performed by my. Some of them in the papers they are refers to another paper, which is a college that he was doing also the characterization. For example, I performed the characterization of SAM and XRD, and those are the ones that I was kind of. Explain more in details. However, I didn't do it of Raman of those because I didn't use Raman spectroscopy. I refer to the paper of my college.
That was not very clear to me. What have you done from these techniques and which has been done by others? Okay. Yeah. Also in the experimental. Yeah, which is the limit of quantification of these 4 antibiotics that you have studied, or the different antibiotics?
What do you mean about
the limit of quantification? Which is the minimum concentration that you can measure? I haven't found anywhere the limit of detection, limit of quantification.
Yeah, I'm not pretty sure exactly what is the limit of quantification of the Q-trap we are using.
So all the samples were analyzed by LCMS, no?
Yes. But I don't know exactly what is the limit of quantification. What I can say is not that sensitive, for example, in PTTs or...
No, since the starting concentration is quite low, no? It's 200 nanogram per liter, well, nanomolar, no?
Yes. It's 0.2
micromolar.
Micromolars,
Yeah.
yes.
We are 98% of removal in some cases, no? This is quite low than the...
But
you are able to detect, no?
Well, it's not much.
To quantify. Okay. In the determination of the electrochemical surface area, okay, You mentioned you have you do a ratio between the double layer capacitance and the reference capacitance. Yeah. You mentioned 10 microfarad per square centimeter. I don't know if you have this value in mind or not.
Yeah,
Okay.
yeah, I think I
because
remember
I don't
it.
know, this value is referred to which kind of material?
Carbon materials, yes.
But it's planar materials, I suppose, no? Or is this for porous materials? Or?
I think I will say it was porous carbon materials, but I'm not pretty sure.
Okay. No, because I haven't.
But yes, I remember this value.
Okay. Okay. What about, you mentioned something in the conclusion or perspective. What about the stability of the electrodes? Because somewhere you mentioned, oh, these are stable, no? But I mean, long-term stability, which is the main mechanism for the lack of stability of the materials? Is chemical, is electrochemical, is mechanical?
Well, we didn't perform a specific study of stability. However, we can kind of measure or affirm that they are stable because we are using it in many runs, and they are always more or less in the same degree, in the same values of potential. Okay. So, but we didn't perform a specific, how can I say, experimental for it. Okay. However, when you can easily, also we measure as well the release of, in case of sulfur, in order to see if the coating, it was stable or not. We also measure sulfates at the highest current application, because in some cases, in the synthesis, we didn't have stable coatings, and we were releasing our coating, and this is something that makes the electrode unstable. However, we didn't perform a specific study of in a long term, I will say. Okay,
so it's something that must be studied.
Yeah.
I have some quick questions to finish. I don't understand very well in the synthesis procedure of the reduced graphene oxide. I mean, how is reduced form? Which is the reductant?
It's reduced in the hydrothermal treatment, because we are using an acidic solution of GO, and we soak the mineral wool in this solution, and through the temperature in the hydrothermal treatment, due to the high pressure and temperature, the GO is reduced to RGO.
Without any reductant in the...
No, we didn't add anything. It's just...
Okay. Why using reduced graphene oxide modified with these elements instead of graphene oxide?
Sorry?
Which is the advantage of using reduced graphene oxide modified with these elements instead of using the same elements modifying graphene oxide? Which is the interest of reducing?
Reducing graphene oxide because, well, it's a carbon material which is in comparison with other anodic materials, or in comparison with...
In comparison with graphene oxide.
Okay, sorry. Okay, so graphene oxide is insulator, and in case of reduced graphene oxide, improves the conductivity. And still preserve some oxygen groups, which are important for the different interaction with the contaminants, but especially because it's a more conductivity material.
Okay. You mentioned several times that one of the advantages is that you don't produce chlorinated byproducts. And you attribute this to the lack of electrocatalytic activity of these anodes toward chloride oxidation, right? Is this right? Or, okay.
Yes.
But ozone cannot oxidize chloride and produce these chlorinated species?
Ozone, yes, in higher doses, but we are not producing that higher doses. Okay. Yeah, if this is one of the limitations of, for example, ozonation treatment. which in some cases, depending on the matrix, you need a really high dose, and that can favor the formation of chlorinated
But
oxide.
have you measured any chlorine? I mean, have you experimentally measured?
Yes,
some
yes, we
chlorinated?
didn't report. First, we again do it in the past when we were starting with these materials, and we were measuring the chloride at different current and also in different flows from the anode to the cathode and from the cathode to the anode. And the quantity, if I'm not mistaken, it was, in case of anode cathode, it was 0.1 milligram per liter. It wasn't a significant quantity of so according to this result, we decided to continue with this synthesis and these electrodes. And since then, we are sometimes performing the quantification, but also my college also measured the chlorate and perchlorate through high pressure ionic chromatography, and they didn't find anything. And in order to be also confirming this, a CV was performing high concentration of sodium chloride, and we didn't see any peak of oxidation.
Okay. Well, and my last question. I have understood that in the reactor, the anode and cathode are separated by a polypropylene mesh?
No, it's a mesh, a mesh of I don't remember. I don't know what is exactly the material, but it's a mesh which insulate the cathode and the reference and the electrode, which is kind of net of polymer, but I don't know exactly. I don't remember the
It's not
material.
Polypropylene.
Or to be honest, I don't remember.
Probably yes, but
okay.
Is this a mesh that is? I mean, it's porous, no?
Yeah.
But the insulating effect of this mesh is not. I mean, a problem in a low electrolyte medium that like you are using. I mean, it's adding resistance, no, to the system, to the electric field between the anode and cathode.
Well, I think it's not that actively participating on the resistance because I don't remember which is the material, but I don't think that is an insulator because in that case it's probably separating the different compartments, but also reducing the conductivity and but I don't think it's not actively participating on the resistance, or at least we don't take into account this factor.
Okay, I have many other questions. Okay, but I'm going to leave my colleagues to continue. Thank you very much, Natalia, and thank you, Jelena.
Okay, thank you, Ignacio. Now, Radjenovic.
Thank you. First, I would like to thank Jelena for inviting me. It's the first time I am here, and it's for me always very interesting. Subject like electrochemistry for water treatment. I am very happy to say I'm in the same juries as Nacho and Christina, whom I know for 20 years. Okay, I would like to congratulate you, Natalia, for your presentation. It was very dynamic. We see that there are a lot of work, experimental work, and I suppose that it was not so easy every day, in particular with the biology and bacteria and so on. It's not my topic, and okay, I can imagine that to have the same results, it was not so easy. because I am here, I must to give you some questions. I have some common questions with Nacho, and maybe I would like that you explain more, especially to the why the anode is doped with boron and why the cathode is doped with nitrogen. It's logical. You explain us that there are some data in bibliography, but physically, why nitrogen is good for reduction and why boron is?
Well, nitrogen is doped as a cathode because favors the formation of hydrogen peroxide through the reduction of oxygen. So that's why we decided to use it as a cathode. And boron, because experimentally we were previously working with boron in pharmaceuticals, and we decided to try with antibiotics the same configuration.
There is another explanation, the physical explanation is that if you compare the electronic structure between nitrogen and boron, boron has less electrons than carbon. So when you replace carbon with boron, there are some holes, okay?
Yeah.
And so there is
Yes.
P conduction.
Yes.
And it's good for oxidation because you
because
understand.
it's more conductive.
And nitrogen,
yes.
You put more electrons in the structure, so reduction, you know that reduction is to gain electrons, so it's easier, okay?
Yes.
Physically, you can explain that.
Yeah.
Okay?
There are these differences as well, yes, that's true.
Okay. Regarding the graphene-sponge, in your literature review, you write that unlike traditional carbon-based materials, graphene-sponges have exceptional electrochemical stability without corrosion. What do you mean by exceptional?
Well, they are stable. They are. I was trying to show up. No, they are really stable.
You
maybe I was
enthusiastic. Okay.
Yeah, really enthusiastic.
I understand.
Yeah. Yes. Yeah, probably this. But they apparently, according to our experience, they are quite stable, and also the coating is quite stable because we don't have a release after many runs, and this is sometimes kind of difficult to get to synthesize.
This is maybe an information which miss in your manuscript is the duration life, the service life of your electrode, because when we think to the scale up to an industrial process, we need some data.
Yeah.
And for example, your PhD, the duration was 5 years. It was the same. You used the same material during your 5 years, or
no?
Sometimes you have to regenerate.
Yeah. As I was mentioned to Ignacy, we didn't do this study, and it's something that we are probably take into account because now we are trying to scale up these materials as well. However, of course, yes, I was changing the electrode from time to time, but also because the material, the stainless steel that we are using as a current feeder, is also corrodes a little bit. So that's why we also have to change somehow the setup. But no, I wasn't. I didn't work with the same electrode for the whole PhD.
Yes, and is there some irreversible corrosion, for example, with the sulfur graphene or not? For example, you polarize with your electrode and then you stop. Do you have take exactly the same material for another experiment, or you use another one?
Yeah,
It was
no, I
not
was
so clear in the
for
manuscript.
different experimentals. I was using the same anode sometimes. Yeah, I mean it's not for one use. I have been using the same synthesis, a synthesized electrode for many experimentals. And we didn't see we didn't see any like significant change on the potential, so that's why we assume that they are stable, and also neither a release of coating of IO, or for example, if I dope with sulfur, we were measuring the sulfur after the highest current application in order to see if we have a release of the dopant, and we didn't see neither.
That's important, that your potential doesn't change. This is
Yeah, this is the way
yeah.
how we are assuming that it's extremely stable.
Okay.
Or
regarding the mechanism, okay, you present two types of mechanism of oxidation: direct electron transfer or via oxidant, which are electrogenerated. For me, it was not so clear when there is electronic transfer. How to distinguish electronic transfer than reaction with hydroxyl radicals?
yeah, this is a bit complicated to distinguish, because to measure the direct oxidations, we will probably need linear sweet pole tamperometry. And in that case, it's really difficult to distinguish, because the oxidation of our antibiotics usually occurs in the same peak of the oxygen evolution reaction. So for that reason, we cannot really quantify which part is direct oxidation or which part is.
Because today I said that you said that okay, there is adsorption, so there is electronic transfer, and in particular with sulfamethoxazole. And in my experience with using boron doped diamond, with sulfamethoxazole, we had on linear sweep voltammetry, we have a very high peak, which is very separated to the oxidation of the solvent. So it means that the direct electrode transfer is possible with sulfamethoxazole, and there is no adsorption in your case. Okay.
Really
Yes. Regarding hydrogen and yes, you explain that with higher current, it leads greater production of bubbles, hydrogen and oxygens. It's why the higher current causes a decrease in the removal of some antibiotic. It was in page 100. Okay, you increase your current, and the removal is not so good after a certain value. Okay, but it was not the same case for each antibiotic.
Yeah.
And this is why I didn't understand how can you explain that it is not the same case for sulfamethoxazole. It was the case for erythromycin and trimethoprim. Okay, it decreases when you increase a lot the current density, but it was not the same result. Was not for the sulfamethoxazole. Why the bubbles? The role of the bubbles is not the same depending of the compounds. Do you understand my question? Maybe it's too long.
More or less. I will try to respond. I think the bubbles are an important factor on that because they block the active site of the electrodes. However, I also, on the other side, I consider that the different physicochemical properties of each antibiotics also affect to how they are absorbed or attract to the electrode, and if a limited absorption antibiotics is less attracted, probably it will be more even more limited by the bubble formation.
Okay. Because for me, bubbles, it was a mechanical activity. So I didn't understand why adsorption, when the compounds are adsorbed, the oxidation is lesser than when for sulfamethoxazole, it's better. So it's not so clear for me.
Can you repeat, please, because I didn't get
For
the
me,
point.
the bubbles disturbed the
Yes.
oxidation because of mechanical
Yes,
activity.
yes, totally.
Okay?
Yeah.
There is no contact between electrodes or hydroxyl radicals and the compounds. Why sulfamethoxazole, which is not adsorbed at the electrodes, can go to the electrodes to be oxidized
You
better
mean
way than the other antibiotics.
you mean that sulfamethoxazole, which is less affected by the bubbles when you increase the current?
Yes.
Because maybe sulfamethoxazole is the application of current is another phenomenon than the absorption. So, sorry, because I was responding regarding to the absorption and it's different. Maybe the application of current in case of sulfamethoxazole probably is, even though the bubbles are kind of disrupting the mechanisms, the antibiotics, they also react easily to hydroxy radicals or lower. So probably the kinetic of sulfamethoxazole maybe is higher to hydroxy radicals and is more affected by, enhance the elimination of these antibiotics by the application of currents. That can be a...
Could be.
Yeah.
Okay. Yes. Adsorption is a great phenomenon in your study. So when we start a study on adsorption, we study very often the kinetic of adsorption, and we plot isotherm, okay? To determine the number of sites. Okay, my question is, do you have any idea whether the graphene sheets were saturated by your antibiotic?
Well, we can see if they are saturated according to the OC during the open circuit conditions. For example, in case of the experimental we did in order to study the impact of current, some of them were partially saturated because the differences in the absorption of the contaminants. So we didn't perform a specific study about it, but if you are running the reactor, you can see that they are partially saturated or saturated.
Because the duration of your experiments were very long, 28 hours, so I can imagine that sometimes...
Okay. Yeah, so in this case, in this experimental part, we could see that we were trying to partial saturate the sponge in order to see the mechanism of the impact of the current.
Okay. Yes, to regenerate your material, you use methanol. Do you?
Yes.
Okay. Have you measured natural desorption? I mean, only with water or with the buffer solution? Or no?
No, we didn't do it. We just tried with this protocol, which it was just a confirmation of the elimination, the degradation, but it's not really. I mean, it needs a further improve the protocol because it was also used for those antibiotics which were really adsorbed onto the sponge. For the others, we couldn't see anything like. So yeah, it was just a trial to confirm the differences between the removal.
Yes, on slide 18, regarding the comparison of the removal of antibiotics in drinking water and buffer solution, yes, the applied current density were not the same.
Yeah, we couldn't go higher because of the bubble formation and the low conductivity in water. We had a lot of bubble formation, and that's why we just go to the highest current, but it's not the same as a phosphate buffer because since the conductivity is half of it in case of drinking water, we are producing more bubbles and it's more resistant, the system.
Yeah, I understand, but is it easy to compare if the current you applied is not the same? Because you didn't put the same quantity of electricity. So maybe the results obtained with 144 ampere per meter square are better because there are more electricity. Do you understand?
Yeah, but even though the current is higher, what we were proving here is that lowering the conductivity limits the electrochemical oxidation treatment. We couldn't go farther than 86. So we were using this comparison, but just to affirm that is something that that clearly affects the ionic stress to the electrochemical treatment.
Yeah, but there is a consequence on the energy consumption.
Yeah.
In the process.
Yes, totally. Yeah.
Okay.
Yeah.
Okay. Yes, it's not shown here in the slides, but in a figure of your chapter 4, you present it was the figure 5.2. You present the Nyquist diagram and the equivalent electrical circuit here. And there are 3 resistance in the electrical circuit. And if I see the diagram, there is only 2 resistance.
Yeah, we were using this circuit because it was the one in which we get a better fit of the.
Yes, but resistance is the intercept between the signal and the x-axis, okay? So here you have only 2. So maybe you have to change maybe your...
maybe for a word mode and another parameter. Well.
Okay, and maybe the last or the 2 last questions because it takes time. Yes. For example, you have shown that functionalization with sulfur increases the absorption of most compounds with the electrode, okay? When you functionalize with sulfur. Do you have an idea if there is natural organic matter, for example, in the solution, in the water?
Yeah.
For example, humic acids.
Yeah,
Do you have an idea of the consequences on the adsorption?
Yeah, probably is competing with contaminants, but we didn't use this matrix on our experimental. But yeah, of course, the water matrix is always affecting the via compete of absorption
yes.
with the contaminants.
Or with the other antibiotic. Maybe
Yes.
there is a competition.
Yes,
between,
yes. I mean the contaminants,
if
the
you
antibiotics.
put a cocktail of
Yes, yes.
a lot of antibiotics, maybe it will be different. The results will be different.
Yes,
So it's
yes.
a perspective of your work. Okay.
Yes.
Okay. No, okay. I think I have one or two, but I think it's enough. Thank you. I would like to congratulate you once more for your work.
Thank you.
Well, thank you. Well, now it's my turn. Yes, firstly, I would like to congratulate you on your presentation. Good speech, good slides, and then congratulations. And I would like to extend my congratulations to your supervisor. And thank you for inviting me, yes, to stay here today with this jury. No? Some of my doubts have been solved during these almost 40 or 50 minutes. I don't know. But let me ask you some questions. Yes.
Of course.
Well, there are doubts, not very, very important question, but let me say general, okay? Well, in the introduction and during your speech, you emphasized that one of the important aspects in the electrochemical oxidation is the selection of the electrode materials. Mm-hmm. And you said that one problem is the high price of some of the materials available in the market. Yeah, you mentioned something, the price of the bond-up diamond, and other problem is the formation of chlorine byproducts. Mm-hmm. I feel that in literature we can find a lot of work based on the study or the design or the synthesis of different electrode materials. Well, they are focused on the reaction engineering, but this is not in parallel with the development and optimization of electrochemical reactor. And maybe just to solve the problem of antibiotics in waters, this is maybe not more relevant, but at the same level that the optimization of the electrode material, no? What's your opinion in this point?
About for scaling up the...
No, it's the design of the electrochemical reactor. How how does it influence?
In the scaling up, I will say that is one of the major limitations is the energy consumption, which is increasing, and also the mass transfer. So something that I think is more, instead of scaling up, like use modulating, like different stacking of different, how can I say it? Reactors, instead of the idea of scaling up one reactor.
But it's not only the size of the reactor, it's the design of the reactor. I mean, yes, you, for example, you select
flow through,
you
which
selected
is
a flow through reactor in comparison with a
flow by.
Yes.
Yeah.
And did you measure the mass transfer coefficient? Because you say that the mass transfer is improved significantly with a flow through reactor. But did you measure this?
The coefficient? No, we didn't, because we didn't compare neither the one reactor with another.
Yeah, but your criteria or your criterion, one
Yes.
of your criterion is that the mass transfer is improved.
Yeah, because in literature you can well, in the literature you can it was reported the higher efficient of the flow-through reactor because the flow goes directly through the different pores of the electrode instead of going like superficially, and the this boundary layer thickness is lower in the flow-through, so the contact with the contaminants gets better and therefore the efficiency of the treatment.
Well, the content, of course, and the mass transfer. And I miss in the document and in your presentation a detailed scheme of your electrochemical reactor. Sorry. And I don't know if you can explain just a little bit how is the electrical connection, how is the electrode, in fact, because you mentioned the area, but the external surface area, the electrochemical active area, which is an how it
well, an image of the electrode is there, for example, you can see, and it's the reactor it's characterized by like kind of this shape, and is separated by this mesh, and the reference electrode is in between. And with this, we put like material in the well, it's in this. How can I describe this?
How is the electrical connection of the electrode?
The electrical connection is the working electrode, which is in which we apply the current, is the working electrode, which is the anode, and then the reference.
Yes, but how do you do the connection? Just you have your wire and just
with a crocodile. We are using the stainless steel current feeders, and we use the crocodile, the connection from the anode to the potentiostat.
Okay, and we have a good current distribution.
Yes, and also the current feeders are this shape, which are like some different.
And these current feeders are in contact with the water?
Yes, that's why we also have. We are using stainless steel.
Then of this current feeder.
We are using stainless steel because it's a kind of low-cost material, which is kind of not corrosive.
Which is your real electrode, the current feeder, stainless steel current feeder, or your sponge electrode? This current feeder is in contact with water, then you add a
it's I mean, well, the electrode, it's the material which is in contact with the metal which feed the electricity.
Another question: which is the thickness of your electrode?
1 centimeter. Yeah.
1 centimeter.
Half. Yeah.
Yeah. I say this, or as I ask this because maybe you can use your electrode in an electrode membrane electrode assembly and use this in another concept of electrochemical reactor, and maybe they can work properly, with low conductivity water. I don't know if
in electrode membrane.
Yes, in the last years, in this kind of reactor based on PEM, the PEM concept, in which we have the assembly of electrode membrane and electrode, then the membrane acts as a solid electrolyte. And they can be used, yes, in the case of they can be used to treat low conductivity water. then maybe it could be an option just to use your electrode in a different concept or electrochemical reactor. I don't know if some of your group is working on this topic, or all of you are using this kind of flow-through reactors, or
Yeah, well, in the lab scale, we are all using this setup.
okay. Regarding the operation mode, you propose, or you propose and you use always continuous mode, no? And you run your experiment during, I don't know the hour,
It depends of the experiments, but
until attain the steady state condition. And
Yes.
then you have only a final result, a final.
yes, we usually wait to the steady state conditions. But for example, in case of the experiments that we perform using the sponge, we were partially saturated. We didn't get these steady state conditions because the sponge were partially saturated, but in this case we were just evaluating the impact of the current. But usually, yes, we work on a steady state condition when we apply the current.
Let me check my notes, sorry. Well, regarding absorption, the absorption is a very key point in your process. No? I'm right. You evaluate the capacity of absorption of your material, and you extract with methanol the amount of antibiotics retained in your material. But after the treatment, you evaluate again the amount of organics retained in your electrodes. The nature of these organics is the same.
I didn't get the
I mean,
question.
you have your electrode materials, then
Yes.
your pass your solution, and you have the absorption of sulfomethoxazole and the other antibiotics, okay? Then to check this absorption capacity, you run an experiment without current, right? And then you extract the amount of antibiotics absorbing.
Well, we
Just
did.
to quantify more or less.
No,
or
we
not.
quantify all this in the
The final.
Q-trap. The samples are quantified, and the extraction of methanol it was just performed once to kind of confirm the degradation of the antibiotic. But we usually take the sample during the open state conditions, and we use the liquid chromatography and mass spectroscopy to quantify the percentage of removal during the open circuit condition, normalizing this to the initial condition.
Yes, but at the end of the treatment, if you measure the type and the concentration of the pollutant retained in the electrode, you will be able to determine the main reduction, the main byproducts, maybe, or not. Without current, your electrode retain antibiotics. And after the treatment, you have applied the current and you have the degradation process.
Yes, after,
Right.
yes.
Then, I mean, which are the organics retained in your electrode at the end of the treatment?
You mean the transformation products of the...
I mean, you have the raw materials, or you have retained and absorbed it on the electrode transformation product? Have you checked it or not?
The transformation products that, for example, in case of erythromycin, what we were doing is we used a syringe in between the anode and the cathode, and we were studying the transformation products in between. And we were quantified the transformation product through liquid chromatography and mass spectroscopy. And after the cathode, but when the current was applied.
My question, or this question is related with the mechanisms, the main mechanisms involved in the degradation process. I don't know if it is the direct oxidation of the antibiotic on the electrode. In this case, you have to observe that the final products are different than the raw material retaining of the electrode.
Yeah.
Or if the mechanisms of or if the main mechanisms is the indirect oxidation by the ozone or the hydrogen peroxide produced in the cell. In this case, maybe the final product will be retained on the electrode will be almost the initial raw material.
Well, we just studied the transformation products in the case of erythromycin, and according to the transformation product, we could observe that different oxidant species were participating, comparing the fragment that we were observing after the anode and after the cathode. But apart from this, we didn't study in details the different transformation products, which in case of the rest of the antibiotics.
You have to regenerate your electrode after each treatment. You run some kind of electrolysis, maybe in sodium sulfate solution.
Yeah, we clean the reactor, and when we start again a new experiment, we first run with the electrolytes, and then we add the contaminants.
Regarding bacteria, I have also some doubts about the role of the oxidant. Have you run any experiment without bacteria just to check the real concentration of oxidant that you are able to generate in your system? Because the values, the concentration that you give in your tables, this correspond with the oxidant that remain in the system after the treatment, as the oxidant that have not been reacted with your pollutants.
Yes.
Then have you run any kind of blank test just to check the concentration of oxidant that your electrodes are able to generate?
No, we just I mean, all the concentration of oxidants are not measured when we are in the middle of the experiments. We are passing in case of for example, hydroxy radicals, we are using the phthalic acid, and we prepare the solution without any other contaminants inside. So we are measuring the blanks somehow. So this measure is the oxidant species that we are producing, like the blank.
Not the ones. You measure the oxidant not during your experiment, just in another kind of test?
Yes, yes.
Okay,
because for measuring the for example, in case of hydroxy radicals, we need a specific reactant which is reacting with the hydroxy radicals, and then we measure by UV visible, and so it's another set of experiment. It's not occurring simultaneously.
Okay. And you mentioned before that the electroporation is the main responsible of the inactivation of the bacteria?
This is my hypothesis. Yes.
Your hypothesis, okay.
Yes.
And but the mechanism of how ozone or hydrogen peroxide can inactivate the bacteria, the way could be different, or they act in the same with the
They
same
attack the internal part of the bacteria. But electroporation is a phenomenon which occurs like through a clearly formation of pores in the cell structure, which is different.
the membrane of the bacteria.
Yes, exactly. And is through scanning electron microscopy we could see the different pores.
Okay, just to conclude, one or two questions. In the sequential configuration, why did you choose a series sequential configuration and not working in parallel?
You mean in...
Yes, you work with two cells in series, but did you check how it works in parallel? The result
in the two sequential reactor, because we want to have two flow-through reactor in the same configuration, because we already studied like this from flow-through from anode to cathode was the best performing electrochemical treatment. So that's why we just assemble one and the other, like in...
Okay, but another option is just to work with the two reactors working in parallel.
Yeah, but...
you divide the inlet?
Yeah.
Then?
Yeah. And then connect the one inlet to the other.
No, this is in series.
Yeah, because in parallel it will be like one and the other separated.
Yeah.
Yes. Well, no, we didn't perform this study, but
okay. Don't worry. In this case, and in the case of using intermediate current, you said that the lower log removals may be explained by the retention of oxygen and hydrogen bubbles in the second reactor.
Mm-hmm.
But do you stop also the flow rate? No, you only stop the current.
No. Yes, I mean...
you use intermediate current. Then
yeah, we stop the current. Yes.
You only stop the current.
Yes, because if our materials has capacitance, they are, even with the current switched off, they are still degrading. But
but why oxygen and hydrogen bubbles are retained in the second reactor if the water is fluxing?
Yeah, but because we are producing bubbles, and bubbles can be like accumulating in the reactor, even though the
but
flow...
it's a flow through, and you have the
Yes,
water passing through the electrodes.
Yeah. But
then when you connect again the current, you see a high bubble flowing up.
No, the oxygen evolution reaction occurs when you apply the current. So
Yeah.
most likely we are producing these bubbles, and these bubbles are blocking the active site at the highest current. So this study was performed at the highest current. That's why probably it's a matter of oxygen evolution reaction, which is accumulated in the reactor, even though it's flowing.
But you say that maybe I didn't understand this correctly. But you say that you retain this bubble when you switch off the current, but the water is continuously fluxing.
Yeah, but maybe is even when the water is fluxing, sometimes there are some bubbles still retaining there. But yeah, maybe during the I understand your point that if the current is switched off, those bubbles are not producing in this moment, but probably they are still retaining somehow.
Okay, well. I have some question, but maybe later during the pika. Okay, then that's all from my side. Thank you very much. And I think that, do you have any other question or some doctor in this room?
Yeah, I have, sorry.
Okay.
Yeah, it's just two very short questions. Is there any correlation between a more resistant bacteria to antibiotics? Is a more resistant bacteria to degradation or not?
Well, this is a difficult topic because the resistance of bacteria change some part of the, can change somehow the structure of bacteria, but in some cases it could, I think, because we didn't study in details, it's something like more from the, out of our topic, but probably that change could compromise the effectiveness of the treatment or probably not, because we didn't go into this
the other
topic
question is,
in details.
you are proposing a method to inactivate bacteria, so you open them, so I assume that you release antibiotic-resistant genes, no, to the solution?
Well, yeah.
So it's contaminated with this, no? Do you have a TICRA? Is there any group working on this kind of analysis? Of?
Yes.
Okay. Okay.
Yes.
So,
yeah, that's why I mentioned that, well, I mean, of course, everything that we are producing afterwards is autoclaved. And, well, it's not directly released into the, it's treated. But it's important that's why as a future perspective, a safe treatment has to consider also the fact that we are releasing antibiotic-resistant genes and what to do with this contaminant, which are also in some studies, electrooxidation studies, they are also degrading these antibiotic-resistant genes. It's possible to degrade from electrooxidation process. So most likely they are also degrading, but we were not able to measure it, even though we tried to do it, because we designed a protocol that in the end we have to improve this protocol because something was, wrong. We couldn't do it in the end.
Well, thank you, Natalia. Now I think that it's time for a short deliberation, and we will come back in a few minutes, okay? Thank you.
Jelena, cuando me ha dicho...
No les he dicho que tienen que votar después para acumularlo, que no me vengan con...
Ah, vale.
Well, let me speak now in Spanish just to communicate you your qualification, okay, your final mark. Bueno, tras una breve deliberación, ¿vale? Todos estamos de acuerdo, bueno, que en este acto, en esta defensa, tu tesis doctoral merece la máxima calificación que podemos otorgar en el día de hoy de excelente. Así que felicidades, Natalia. Ya veo que durante estos 5 años has hecho muchas amistades, eso está bien. Muy bien, pues yo creo que poco más. Bueno, ya sabéis que el voto del cum laude se emite en secreto y se comunicará con el procedimiento que haya establecido a lo largo del día de mañana, posiblemente. Y nada más. Por mi parte, damos por concluido este acto y ya podéis pasar a felicitar a la nueva doctora.
Ay, con micro, venga, va. Feels like singing, ¿no? En castellano, ¿no? ¿Mejor o English? I don't know. No, por castellano, sí, por los padres. Pues ha sobrevivido una tesis conmigo que ya es mucho. O sea que... Sí, sí. Bueno, creo que todos mis estudiantes lo tienen complicado por el tema que tienen. O sea, no hay nada, digamos, conventional que hacemos, pero tú, además de intentar sacar adelante tu tesis, tenías que luchar un poco, creo, contra ti misma. ¿Eh? Y bueno, y creo que has evolucionado mogollón. Eres mucho más optimista ahora que antes. Pues nada, y bueno, felicidades a tus padres también. Ya está, una doctora, no sé qué más, ya está.
Bueno, yo si queréis digo algo. Bueno, ¿tenéis tiempo? No. No, solamente quería agradecer a mi supervisora y especialmente a todas las personas que están detrás de no de la tesis doctoral, sino detrás del día a día, que son, que es quien me sostiene y quien hace que todas estas cosas sean posibles. Y nada, que muchas gracias, de verdad, que ha sido un placer compartir todos estos años con vosotros, vosotras y vosotres. Y ya está. Y vamos a echar una birra.